Welcome to the Practice Podcast, conversations probing the nature of practice. I'm your host, Dave Fearon, co-author with Peter Vale of the digital book on Practice as a Way of Being. Find it at mylibrary.world. And now to our show. Here's another episode of Dave and Dad. I'm Dad. And Dave is the one who does a lot of thinking about everything connected to the basis question, which is social inaction. How does it work, particularly in conversation? And how does that relate to practice? So Dave keeps finding a new frontier for thought on this, and he'll share that with us now. Welcome, Dave.
Hi. For all of our fans, we
do.
we've been building up quite a collection now over maybe 4 years. And they're consolidated a little bit on our webpage, but also on YouTube. There's a particular playlist, but I try to make these talks somewhat self-contained, although this one will be delving back into a couple of times that we've gone into physics, various models of physics. The reason for this is even though what I've been calling enacted social action is a kind of, I guess we call it a sociolinguistic theory and a way of looking at human group life and social organizations at the level of conversational communication in particular. There's been a growing area of research in cognitive and neuroscience and some other fields where the concept of inaction itself has become more widely used and pretty much in the way I started working with it back in the late 80s and 90s. So I think the more that we can make those connections to other areas and fill in the blanks, one day the scholars will invite me to write my books and connect them all together. But
yes,
in any case, for us at least, we just have a verbal collection of the ideas.
And that's, by the way, very good practice for anyone who's cooking, co-learning and co-creating a stream of ideas that eventually could be put into print. But I want to point out one thing about inaction. For years, I would type that word and the spell checker wouldn't allow it. They would say, no, they'd change it. And then finally, I noticed recently that inaction, ENACTION, or enact, they're both being allowed by the new spell checker. So we've broken through.
And I still find that my kind of metaphorical definition works fairly well. I have specific definitions for different applications, but the metaphorical level definition draws on its three meanings that you'd find even in the dictionary, which is enact is to perform. So, which means in the broadest sense, actions, things that happen. And what we'll talk about today is things that really happen, like physical reality. We wanted to be able to connect to that. And then inaction also refers to bringing forth something in the sense of emergence, which is important to think of layers upon layers of organization that in this context can help explain social organization, but even might drill down all the way to systems at their quantum level. And so we're going to get into that a little bit more. And then the third definition of enact is to as though enacting into law, making something law-like, which I
Right.
like the broader term warranting, being able, and and in a more physical sense, anything that's kind of using its own history as a justification for moving forward, but not an instruction, not like a fully determined instruction for moving forward, but something that's referred to, um, that and could be referred to by more than one person, for example, as justification for moving. Well, you could kind of extend this analogy all the way to physical things, physical systems, even very simple ones in interaction, using their history as a basis for prediction of a certain sort
Hmm.
to allow actions to go forward. And interestingly, this idea even of history, a deeper history in time mattering to physical systems isn't clearly present in basic quantum mechanics. And if we get to it, I've been following someone who's using a different way that we've been invoking Markov statistical dynamics as a reason for questioning whether maybe the 100 years of thinking in quantum um, mechanics is actually kind of a reification of mathematics.
Hmm.
Certain aspects don't exist in reality, and he's got a better way of doing it, but we'll
Hmm.
see. So I talked about physics in 3 episodes so far. An early one, episode 178, I talked about David Bohm, his
Yeah.
approach to quantum physics. Typically, it's called pilot wave theory. And he also talks about implicate and explicit order. Um, and I kind of took it into esoteric areas like the holographic properties of the brain.
Hmm.
And I won't reiterate it much here. I might invoke it a bit because he had an interesting. He was one of the people who took some of the woo factor out of quantum physics, which we will be talking about here and there. Facts such as a requirement to explain the improbable the fundamental improbability of how quantum systems will collapse from an entangled state. Some very accepted theories say that this requires multiple universes, so that every time uh, two atoms interact or two electrons, if they can have two choices in their outcomes, an entire new universe is created. And so every decision and interaction in the world creates multiple universes. And it even requires apparently universes back in time because of the way the math works out. And that's a still accepted. It's called the Everettian position. Um,
Hmm.
but it requires certain assumptions, and Bohm had some good alternatives requiring something he called generally referred to as hidden variables that unexpressed somewhere in the unobservable elements of quantum change, there's basically what came to be called a pilot wave, kind of an additional guiding uh, source of information that makes the appearance of things like two particles being in the same in two different places at the same time be uh, better explained as kind of this third principle.
Hmm.
I won't go into it too much, but he there's always been a critique that there can't be hidden variables in a good quantum theory. Um, but what they've lost track of perhaps is that there can't be there may not be hidden variables in certain mathematical expressions of quantum theory, but that doesn't mean there aren't in reality. So we may end up there.
Okay.
I did another episode on time and George Herbert Mead, the American pragmatist philosopher's idea of the specious present, and then physicist Carlo Rovelli's book on time called The Order of Time. We won't get
Mhm.
into that. We won't have time. But uh, it, I was tempted. It kind of ties into some other people I've been following. And then, but what I want to focus on is one I did just under a year ago, last March, episode 256, which was on the nature of information.
Yeah.
And in that episode, I looked at one of the key um, components of enaction theory is autopoiesis theory, which is a theory that explains the special qualities of living systems um, down to any level where there might be apparent threshold of living systems. This was developed by Chilean biologists Maturana and Varela, mostly in the 80s, um, late 70s and 80s. And then in that episode, I extended their work towards more recent work by Oxford physicist Chiana Marletto and her professor. She worked with David Deutsch on their theory, what they call constructor theory. Her popular science book um, describing that was The Science of Can and Can't.
Hmm.
Um, and it worked well for coming up with kind of a physical explanation of information, and one that works well with the core of um, uh, an action approach. And in that episode, I didn't get into her where they really applied their work, which was in quantum physics. So I might try to detail some of that and see how we can kind of still make those connections into what we're talking about. And then I'm going to talk about one other that I kind of mentioned in an episode called assembly theory. And this is kind of an interesting approach that bridges, I think, this kind of um, the basic physical um, processes that Marletto gets at to what to where you'd get something like a living system, self-organizing living system like autopoiesis, and this is assembly theory, and this is a pretty new approach that kind of mathematically tries to bridge that threshold between basic physical non-living things and things that could properly be called living. So
Hmm.
try to squeeze that in too.
Wow.
Um, and your job is to make sure that I am being somewhat clear because I'm cramming in quite a lot of complex ideas that I don't really know if I fully understand. Um,
Well,
but
cram away, and we'll
as
see.
we,
And if I get confused, I will say I'll give you the code word. Like rosebud or something
yeah,
like
yeah,
that.
we say in Maine, I may not know nothing, but I suspect something.
Oh yeah, there's
So,
always something out there.
um, so, uh, So why do we care about physics? Do we really need it? Biologists, neuroscience, sociologists especially can largely ignore some of the details. But there is a basis for what we've been calling an action that does connect to things that really kind of need a good grounding in physics. Um, the earlier episodes, I talked about some of the core ideas. Episode 162, I talked about the core ideas of self-organizing systems. This was Ilya Prigogine,
Mhm.
did a lot of his work in the 70s, where there are special properties of even chemical reactions where they become what he called autocatalytic, self-referring, that could possibly extend into living systems,
Mhm.
and where autopoiesis covers living systems. These are systems, for example, that um, are able have enough internal parts to be able to reproduce themselves and also reproduce, especially a boundary between what counts as them and not them.
Mhm.
be able to adjust to perturbations, and consume things, what Prigogine would call exporting entropy, by basically taking in new energy and getting rid of unusable energy in the form of
Mm-hmm.
foods for animals. Um,
Mm-hmm.
and and so this too kind of needs physics behind it. How is this actually happening?
Mm-hmm.
Um, and then for getting into the brain, and even social interaction, I relying a lot on Carl Friston, um, who's takes somewhat of a more computational neuroscience point of view, um, towards towards how interaction works. A couple key concepts there are the Markov blanket. This is a kind of a mathematical expression of what would be basically an autopoietic system. It's one in which the system is made up of any number of basically lots of little interacting parts.
Mm-hmm.
Internal to the blanket are various child relations. So you'll have various child-child relations. You'll have kind of as a surface level a parent relation. So you'll have child-child and child-parent relations on the inside, and then but the parent relationships kind of act as a whole towards the outside world. So there's a separation
Mm-hmm.
of the
Mm-hmm.
outside and inside. And so while the child relationships can be very kind of expressed almost mechanically, but in these self-organizing terms, um, they're having very direct interactions with each other, is what Maturana Barrera will call it kind of a structural coupling. The surface of a Markov blanket would have a more abstract relation to its world, because it's adjusting itself not by its different various parts to something that impacts it from the outside, but it tends to adjust as a whole.
Mm-hmm.
And by adjusting as a whole, you have almost this identity function of self-reference. Um, so and self-repair, and part of it essentially is having, in the process of being able to do this, kind of inherent level of prediction based on modeling of the past. Um, and so this is yet another dynamic that kind of needs some fairly deep assumptions about physics, even down to the quantum level, to be understood. For example, cause and effect.
Mm-hmm.
So that's a bit of a review, and I'll try to kind of take us quickly through how constructor theory, what that added to where we were at that point. So constructor theory, this is Chiana Marletto and David Deutsch. Again, podcast 261, I go into more detail, but they're really focusing on taking the fundamentals of physics and down to, kind of not just more math, but what is real, what is possible, and how can you start reframing physics and laws of physics as things that can happen and things that are impossible to happen. Because when you get into quantum physics, you get people getting so involved in their math and then having to make the math more efficient that they have to start introducing things like imaginary numbers. And then they even have to kind of create an entirely represented version of reality that's called Hilbert space. And they'll explain how quantum events occur in Hilbert space, and they can explain it very well with lots of math that proves itself. The only problem is Hilbert space isn't actually real. It's a
No.
representation. And so maybe they've made some kind of lost track of some founding assumptions about what this is. And one of the areas that construction theory kind of builds upon is kind of an information approach, and there's more of an information, even quantum information theories that this kind of falls in among. So the constructor as an information theory concept is something that I had mentioned, goes back to the Alan Turing, the one who was an early inventor of computers
Hmm.
during World War II, the concept of computing, and then physicist Ralph von Neumann before him, um, defining the idea of a constructor. That basically a constructor is anything physical that can perform tasks, which are physical transformations on a substrate, which is then transformed um, by those tasks, uh, and especially transformed in a way that retains the original physical attribute, or which is basic. Well, sorry, it's that a constructor is something that when it's transformed, it will retain its ability to repeat the task essentially. Um,
Okay.
so that there's a capacity for the constructor to act again. So you have this kind of self basic concept of something that could sustain itself, not necessarily with the complexity of autopoiesis at this stage, but just kind of a concept like anything, a molecule. How does a molecule stay intact over time? There's a lot of
Yeah.
things bumping into it, and yet molecules can stay pretty solid, especially in something like a crystal.
Yeah.
So they think about this in terms of, well, how could this be expressed, this sustaining function be expressed as information? And they do it by defining two terms, flip and copy. So the concept of flip expresses the type of configurations that some given system, no matter how small, will express over time. Um, so which is basically the flip is all the things that can do or be done to it without breaking into something else, a molecule breaking into its component atoms.
Hmm.
And then the other idea is copy this. So to sustain a configuration over time, there's kind of is expressing a copy. So that basically it is itself, but copying also can refer to interaction of two systems. So two systems might interact, each one having their ways they can interact expressed as these kind of flip configuration states, which kind of have degrees of freedom. And then if as at the end of interaction, maybe both parts will come away the same, or maybe some will have been changed. But if let's say one molecule reacts with another, that the molecule that is reacting um, isn't fully destroyed, but takes away some of the energy from that original molecule, then there's a little bit of a kind of a communication going on,
Hmm.
where as a result of interaction, the copy state of both have changed, but they still retain some of their basic configurations or flip capacity.
Hmm.
So this is a very raw way of saying something that at a higher scale can be expressed more simply. Like, if you had a traffic light, it has configurations of red, yellow, and green. Um, it can convey information that a driver can copy without destroying the traffic light. So
Hmm.
it's even kind of an abstract way someone can be affected by the flip properties of something else, even at a distance or between living and non-living organisms. Um, so one way they express this is that um, systems, in this sense, if they are able to stay intact, or as they change, they kind of are building. They have this identity function. Um, there's a maybe a persistence in their structure, which they kind of consider being described as a. They use the term knowledge. It's probably a little too specific, but
Hmm.
there's kind of a built-in resilience over time. Um, it kind of explains catalytic actions where you'll have certain um, in chemistry, there are certain materials which will speed the reactions of other materials by basically facilitating making um, their reactions occur with lower activation energy. So there's um, so basically the catalytic action is a type of constructor that can more robustly maintain itself and facilitate the changes of other parts. So, you could kind of start seeing how catalytic actions of chemistry with a little more complexity could scale up to something like self-organization. But we'll get to that
Mhm.
later. Um, Another aspect of the constructor is to think about these flip states as kind of degrees of freedom by what a given system can do. Those degrees of freedom they refer to as counterfactuals, which is kind of an interesting aspect of information that I think also can scale up in a way to other concepts for more complex systems like humans, that you can think of it as what interactions don't are not destructive of it. Well, there may be a range. There may be a range of things that a given system can do. And the fact, and you know, in an actual interaction, they'll do one thing, but there may have been counterfactual things that it could have done as well.
Mhm.
And overall, this collection of counterfactual possibilities also becomes kind of a feature of its identity as a thing. What Not just that it persists, but it starts. You can kind of look at the complexity in the things that it can do. Um, and Even though this sounds confusing, it's actually a way of defining causality in a less abstract way than many other areas of physics do, including things like classic Newtonian physics of, billiard balls bouncing against
Mhm.
each other, but also a lot of the textbook quantum theories also don't really define cause and effect very well. And we'll come back to that, but you could think of the constructor as being the cause of a task. So there's a definite causality in this theory, where the constructor is the only object in the surroundings or domain of what it interacts with that can change something that's coupled to. While part of those properties remain the same. So, the catalyst is an example of that. You can think of, if the catalyst stays intact, it's achieved being the cause of the change that occurred in the thing that reacted to it. And it's kind of communicative in this sense. The cause and effect have occurred in this sequence of flip and copy states, as sort of an information exchange, as I was talking about. So where this becomes important for those who are familiar with other models of cause and effect is that many theories require what's called interventionist notion, in which there's essentially an agent
Mhm.
involved in, kind of metaphorically, in the reason why A changes to B, there's some element C which is causing that to happen.
Mhm.
And oddly enough, a lot of quantum theories rely on this model of kind of an interventionist cause and effect. Um, but it's what it tends to do is end up with something like an observer as a necessary part of why things happen, even at the quantum level. You'll hear this commonly when you listen to people who don't know what they're talking about quantum theory. They'll talk about superposition of two entangled um, electrons. And what this means is that there's no way mathematically to know which is which. Which basically, if you had one of these experiments where a set of electrons are being split into two directions, if they're entangled, there's no way of knowing which direction it will go. You can only measure either its direction or its amplitude or energy, but not both at the same time. There's this fundamental improbability. And what they talk about are entangled particles collapsing. And the reason it collapses is because something has measured it. Mathematically, that's all classic quantum theory has. They say because something has measured it, then we know what its state is. But until there's that particular type of interaction, we don't know what happens. And so it kind of relies. So measurement is sometimes confused with the word observer. So until this event is observed, we don't know where the superposition entangled particle will land on some sort of a surface, for example. And so when you map it out, you'll see these classic interference patterns for these split beam experiments, which gave the idea that particles are both wave-like and particle-like at the same time. The problem is this idea of calling everything an action of the observer gets people to think, well, all cause and effect must have an observer. Otherwise, everything would be in a quantum state, and it isn't. At bigger levels, everything's in kind of this classical mechanics state. Therefore, there must be observation, and it must be the mind of God observing everything that interacts. I mean, that's kind of becomes the logical extension of that. And there may be a mind of God, but maybe the mind of God does not have to busy itself with making one electron interact with another. The laws of physics can make that happen in a more simple way. So, this is a long way of saying constructor theory at least is one other way of approaching causality, even at the quantum level, that helps explain that. Do we need a check of whether you're following as a representative of my suffering audience?
Yeah. My mind hangs on this idea of constant forward action. This idea that all these things have to continue to move on. And now we go back to time, I suppose, in future time. But it seems like there's no theory that I've heard yet about reversing that. In other words, you go forward, but you can't go back.
Yeah.
And can you stay the same, really?
Right.
And my hunch there is you can't, because of all these agents working and the measuring going on and everything, that even a simple molecule next to another molecule can't just say, well, why don't we just stay this way and be a rock?
Yeah. I mean, there is, it's not there's a whole direction we can go in on that, which I cover a little bit in the episode on time. And it gets a little confusing because at the quantum level, there is a way that might be somewhat accurate that interactions of quantum level particles are actually reversible. And it seems in a sense that they go back and forwards in time. It's called, you often hear the term retrocausality, but it's not quite that. And I think it's too complicated to explain now. I don't
Maybe
understand
what they're doing is just like vibrating a little bit, like instead of back and forth, just like
that's probably a better analogy in a lot of ways. And then, but really what you end up with in most situations, as soon as, apart from things being in superposition, which isn't easy, It's not all that it happens a lot, but it isn't really sustainable. As soon as like two electrons bump into each other, they're no longer entangled. Anything that interacts it doesn't have this magical back and forth time. So at that point, you're dealing with entropy,
Hmm.
which is the accumulation of unusable energy,
Right.
which could also be defined as unusual information in the sense that
Yeah.
tasks are not able to be.
Don't need that anymore. Yeah.
Yeah, and the Carlo Rovelli at least argues, and others argue that entropy is one of the main things that gives an arrow to time. One
Hmm.
way, the idea of entropy is important to understanding, going back to information, like the way that Carl Friston deals with it with Markov blankets, um, because and also Ilya Prigogine, the Markov blanket, one of the things that it would have to do is be able to export its energy, its entropy, because in those like child parent relationships, too many errors basically not just break it apart, but reduce the available energy uh, in the things that it can do. So
Hmm.
Markov blankets, especially for any living systems, are far from an equilibrium state. They're
Hmm. Hmm.
equilibrium system, and that is part of its special dynamics. Um, so if you think of a Markov blanket, you can kind of think of the very simplest ones you can imagine would still have degrees of freedom for what it can do in order to not be destroyed. And these kind of degrees of freedom are what Marlato would call the flip states,
Hmm.
which come kind of the physical information capacity of a Markov blanket. Um, for Friston would tend to think of information in terms of kind of the averaged flipped copy events over time for a given system, um, and and expresses what he calls a free energy minimization principle. Free energy is basically information, the amount of information um, that is predictive of what could happen to it. Or another way of thinking of it is the amount of surprise that a system will encounter.
Hmm.
Um, the It's free energy in that it's kind of the perturbations that could happen, the free perturbations that could happen to a system that the system can't deal with. It's it is following physical laws like the conservation of entropy and entropy of conservation of energy, which is a basic law of the universe, and entropy, another law, and the need for dissipation, and for these far from equilibrium systems. Friston uses mathematical models to express this. The Markov blanket manifests what's called Bayesian rules. Bayesian statistics are basically hypothesis testing. Um,
Hmm.
you could think of this a flipped configuration that makes up a given Markov blanket. Where it is at some point in time is kind of like the initial hypothesis of what might happen to it ahead of actual evidence of an event. So it's almost like a Markov blanket is always physically expressing the likelihood of certain tasks that it might encounter, um, which in the form of events or occurrences, like one bacteria bumps into another and the
Hmm.
other bacteria is trying to eat it. Um, has the bacteria developed defense mechanisms
Right.
for that particular other type of bacteria? Have they evolved? And will it, if it actually survives that unpredictable encounter, so a lot of times it's doing predictable things and it's trying to do as many as
Hmm.
it can. That's the low energy state.
Hmm.
But it also has to be able to deal with novel encounters. And if it's achieving that, at least for its essential components, it's also updating some of its internal flip configurations in like the children
Yeah.
relations.
Yeah.
So in a sense, by encountering something new, it's physically updating its hypothesis in the way it's adjusting to new evidence.
Hmm.
In Bayesian statistics, this is called posterior probability. Um,
Hmm.
so, free energy minimization would be a preferred state. Kind of, if you look at it over time, Bayesian statistics calls free energy kind of the marginal likelihood or probability of predicting evidence under all possible hypotheses.
Ooh.
Um, but this is, I like the idea mostly because it's a way of, not only is it a way of framing in action in real of physical events of energy exchange, right down to maybe simple chemical systems or even quantum level. But my favorite philosopher, George Herbert Mead,
Hmm.
one of the American pragmatist philosophers, his model of action is based on hypothesis testing.
Yeah.
The how he frames the act is
Yeah.
basically people are predicting, building hypothesis of the world, testing the world, adjusting to those.
Interesting.
So, it may be more of a metaphor right down to this, very physical substrate, not just in brains, but really any systems, and maybe not even living system, maybe something below living systems.
Yeah.
Um, So I'm going to get back to constructor theory with quantum, and this may be another long episode, but I did want to drop in here an interesting book I just finished on assembly theory, because
Okay.
there's a little gap. What is this gap between quantum and little molecules bumping into each other and chemical reactions, and then the autopoietic living system that would be recognized as something living? Um, so assembly theory is something that tries to address this by both kind of with evidence and mathematically breaking down what are the actual component actions that really distinguish the threshold between living and non-living things.
Yeah.
Uh,
That's a big question right there.
yeah, and it's an interesting approach. It was pretty much introduced only in around 2017 by the chemist Lee Cronin at the University of Glasgow, Scotland. And then it was later extended by a collaborator at Arizona State University who's an astrobiologist, Sarah Imari Walker. And I just finished her book called, released, I think just last year, called Life as No One Knows It. And why an astrobiologist? Because she was interested, because, looking at, as the Hubble and the Webb Space Telescope now can get more and more details about other planets just from their spectral analysis and other signs, and also, rocks from Mars and other things
Hmm.
have these chemical analysis. How would you know on another planet, or especially far away, whether something's alive or not? Can we expect only DNA to be the sign of life?
Yeah.
Is given that there's a good deal of randomness in why, DNA, our particular DNA, evolved versus some other way of replicating
Yeah.
the basic chemistry of life.
Hmm.
So, for example, back in the around somewhere in the Clinton administration, he got up and announced, "Oh, this meteorite from Mars shows it probably shows signs of life. There must have been life on Mars," and they kind of derived it from things that kind of look like fossils or some
Yeah.
chemical traces. But later on, they decided it wasn't quite a good sign of something having lit, actually being a living system. Um, but Walker and Cronin kind of would look at that more systematically. What is it? What's the difference? And what was happening and what wasn't happening that could really make you find that threshold? And her book kind of goes into various aspects of it. But I like to kind of just kind of get at the core of assembly theory by looking at this notion of flip using the constructor theory terms, flip
Hmm.
and copy,
Okay.
because Walker's book, she does acknowledge constructor theory as being a nice, very compatible, almost predecessor of where they are.
Hmm.
So, um, so again, if you were looking at a system, you can define it in terms of the flip range of possible configurations, and then the copy, its ability to copy itself or capacity to exist over time, any changes that don't destroy those systems, and then you'll have a set of counterfactual possibilities for any given interaction with the world. So if you were to look at, let's say, the evolution of something over time, you just have a series of these occurrences happening, what Maturana and Varela describe as a structural drift, where things kind of evolve, things that are living can evolve over time to more complexity, but they still kind of have that they do it by maintaining this this chain of events all the way back to their origins, really. So what then would be the origins of life on Earth that led to this massive uh, complexity? And was it just random? And they
Yeah.
don't necessarily know the answer to that, but certain aspects of it being random are infinitesimally unlikely. Even with billions of planets in the universe, if it really required of absolute randomness for only RNA, the first bit of RNA to suddenly spontaneously self-assemble before everything else can proceed from there. We would hope that there's more simple things that can kind of be forced by mutual constraints of their interaction into that higher complexity,
Hmm.
so that you can so it doesn't have to be quite as chancy or miraculous to have happened in the first place. Um, so um, as we talked about catalytic reactions as an example of this, kind of keeping it brief, you can look at the difference between a non-catalytic chemical reaction and the conditions that might make it chemical as kind of a step in complexity. Um, and then if autocatalytic reactions can then interact with each other in a way that creates more complex reactions, you might get something that becomes a Markov blanket. And then from a Markov blanket, which maybe can be found in things that seem non-living, you get something that can evolve towards being more self-sustaining in a way that creates a proper membrane for itself, kind of incorporates more of its even its attackers into more symbiotic types of relationships, and then begins to assemble its own means of reproduction. Um,
Sounds like living to me.
yeah. So the book, I didn't get into their actual published scientific articles, getting into the math of this. And probably if I did, I'd just see a bunch of equations. So let's take it for granted, especially Lee Cronin is able to do these cool calculations and uses a lot of uh, powerful computers. And what he proposes is that these steps from basic um, you know, bits of atoms and molecules up to a living system takes assembly steps it takes basically 15 steps on average, 15 assembly steps. So I wouldn't, her book didn't list what all these steps are, so they must be kind of abstract.
Yeah.
But because this is a popular science book, but it at least gives some formulas, so that if you did find a meteorite on Mars, do you see, roughly 15 steps of complexity given some sort of a chemical that maybe could only have been produced by a living thing? Only a living thing could have even left the fossil traces of those particular chemicals stuck together in the way they are. Or if the Webb telescope, like in 2021, it was looking at the TRAPPIST-1 star system, and if it saw lights on the dark side of the planet that seemed too organized to be, a bunch of volcanoes, could they be
Hmm.
signs of industrial society? Only that would assemble such complexity. So you can kind of use assembly theory and these steps as a way of breaking down the parts of the parts of any given sign of life into something that at least gives more of a clue that could be applied to astrobiology, but also to understanding life on Earth. And especially this idea that this, with self-organization and the kind of the resilience of information and the way constructor theory has it kind of helps account for why all of life on Earth could, virtually, all of it goes back to DNA. So once DNA happened, all life on Earth, that was it. That consumed essentially all other ways of doing life on Earth. And
Wow.
on another planet, it could be something entirely different. Um,
Ah,
so, the UFOs that have aliens that look just like us, that if that were true, that means someone has gone and seeded all the planets with DNA.
with DNA, yeah.
Yeah, or they're using special ways of making us think they look like us. So anyway, but apart from, and then she actually goes into the probability of there being life on other planets, and it's kind of hard to say. There's arguments for saying that we're fairly rare, and others saying that there's life everywhere. So maybe this eventually will help resolve that.
Yeah,
Um,
I can, with so much momentum, again, my word, toward higher and higher stages until you're at the life stage. And then once in the life stage, continuing to rise as far as these various factors allow. We I'm hearing that we found this to be going on right here on our little planet.
mhm.
Why in the world wouldn't it be going on in every other formed formed item called a planet?
Yeah, a lot of
This,
them. Yeah, and we're seeing this,
in other words,
this.
quantum physics is all on everything we can
Yeah, that
call
has to be
tangible.
everywhere. That has to be everywhere. I'm pretty much
Yeah,
the same way. And then and maybe these ideas start to show that there is a real preference for ordering. With any interaction as a kind of a real the more just by increasing the energy and adding more constraints, you get spontaneous ordering, and it gets
ordering.
more and more
Yes.
complex, and then starts to build upon itself. And so you get kind of this top-down ordering, extending all the way back from more organized things down to their molecules and atoms, and maybe even
Hmm.
the quantum level. Um,
Hmm.
this is what kind of what David Bohm was talking about is the kind of implicate order that is the hidden variables behind real things as they emerge. But maybe these constructor theory and assembler theory are starting to uncover more of those hidden variables, at least conceptually. Um,
Yeah. Uh,
but yeah, but I did want to squeeze in one more
okay,
one
because
more physicist.
we have time for one more
All
physicist.
right. Because this one's challenging. He hasn't written a book yet. Um, uh, it, it, uh, but he's done lots. I've been listening to lots of YouTubes, especially ones done by uh, uh, Kurt Mungel's very good show, Theories of Everything, where he had
Mhm.
about 10 hours now of interviews with um, uh, this researcher at actually he's a lecturer at Harvard, um, and his name is now I wanted to make sure I have it in front of me in case I have to spell it, and now I can't find it. Oh, Jacob Barandis, Barandes. So he's at Harvard currently, a lecturer in physics and philosophy, and he directs the physics graduate program.
Mhm.
And I think working with graduate students, he's a very clear speaker. Um, I looked at his articles and there's lots of equations, so that
Mhm.
I glaze over. But I understand what he's talking about pretty well, so I recommend finding him on YouTube, some of his talks. And he has, as I mentioned, he's the one who really had one of these reframings of quantum mechanics that takes a lot of that woo factor out of it. Um, but he kind of does argue for those hidden variables like David Bohm was talking about as a way of explaining real things, and they are so hidden. They are actually perhaps in reality, not in some special dimension, extra dimension of space.
Mhm.
Um, uh, so um, and I think we can kind of look at oh gosh, I I kind of skipped over how constructor theory deals with the quantum. So I guess I'll have to kind of weave them together.
Move
Um,
away, and then we'll always
all
loop
right.
back in the next episode.
Okay. So constructor theory is very much a an approach to quantum theory. Um, what I talked a little bit about particles in superposition. Um, if you were to have a set of mirrors and a beam that shoots out little particles at the quantum level, um, and it can go from one measure to another. There's no fundamental way of knowing which one at a time is going to go to. Um, there's also a condition called superposition, um, in which let's say you had if you were to have a photo of someone's face, split it in half, gave one half to Alice and one half to Bob. Bob takes off in a spaceship. If it were a nice big thing like a photograph, you'd always have that correlation, knowing that uh, one half the photograph is always going to be that left half. Bob is going to have the right half.
Mhm.
At the quantum level, splitting splitting something into two particles into superposition where they're entangled with each other. Um, if you had that, like basically Alice has the left-handed spin and Bob has the right-handed spin, they wouldn't know which, if they actually measured what their spin was, they would actually collapse the superposition and it would no longer, it just be basically two particles no longer entangled. So as long as they don't measure it, Bob can go off in his spaceship, be as far away as he likes. And then when Alice measures her spin and finds that it's left side, um, we would know that Bob has the right side spin. But there's is a special strong nature to this correlation where, in a way, Alice's measure at that time instant is thought to, by some of the math, instantaneously change the direction of Bob's entangled particle.
Hmm.
This is called the
No matter how far they are in
Yeah,
space.
so this is called the idea of non-locality, and it seems to violate the speed of light because it
Hmm.
seems like an instantaneous exchange of information. Now, this is just represented by math in a way, and Einstein never liked it. He called it spooky action at a distance. And he wrote a famous article with called the EPR paper, Einstein, Rosen, and um, some guy with whose name starts with P that I can't remember. But
Yeah.
he argued against this, and there's a long, you know, the whole thing that Jacob Brandis gets into about physicist Bell. Gosh, I want to say Charles Bell, um, who wrote some um, classic arguments about why whether or not spooky action at distance was true or not. All that aside, the way constructor theory deals with superposition is it essentially says that these two particles can both have flip states. They have configurations like plus or minus, but while they're entangled, they do not have copy states. They
Ah,
they call it like non-clone. They basically have not completed a copy.
yeah.
Um, and over the course of time, until some other interaction happens in which there's this collapse. And so the it's not that this happens instantaneously in the future. Basically, it's something that already happened at the point, the original point of interaction at which these two particles broke into two enacted parts.
Hmm.
Um, the problem with this idea is that in the classical math of quantum mechanics, it 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 is not easy for them to have a statement of the history of that interaction that would allow the idea that the reason Bob's half of the entanglement was on the plus side was because it already was at the beginning before he left in the spaceship.
Hmm.
Just the way the math works, it kind of forces this idea of the spooky action at a distance. And one reason is goes back to one of the other Markov probability calculations, um, which is called the Markov chain. Um, that um, A Markov chain is describing a system that transitions from one state to another within a finite set of possibilities, or kind of the flip states. But at any given point, the future state of the system depends only on the present state of that system and not on the sequence of events that preceded it. In other words,
Hmm.
it's kind of like every moment is born fresh and new
Yeah.
under a Markov kind of portrayal or representation. So, in a sense, the system's behavior is memoryless. And basic quantum theory kind of relies on this so that you can kind of see a causal chain of events, but it's the math is like each event has to happen fresh. It's almost like if you threw a ball at a wall, the first measure becomes it's hitting the wall. If you threw a ball through the window, there's still kind of a sense in which there's a measure as it's passing through the window, and then another measure of how the
Well,
trajectory continues forward, as though, at any given point, there's some random variable where the ball could go off in some other direction, kind of spontaneously.
hmm.
But the problem where, one of the things constructor theory says is that certain things are impossible for that ball to do. Um, the ball will not go off in another direction. It's going to follow its momentum and path in the classical sense. But in the quantum world, impossible things can happen if you do the math the way it's typically done. And this is why these mathematical spaces don't follow normal space-time, that they have to create something called Hilbert space, which is this mathematical level of reality to which reality is supposed to correspond. The problem is it doesn't. If you're really relying only on this Markov chain description of probability, which is, gives a sense of the fundamental improbability of quantum events. The what Barandis offers is a way of framing quantum events as indivisible stochastic processes. So
Oh.
So that's a new term. It's actually fairly recent math around it. Some as late as 2022. That it expresses it's a way of, but it's basically a way of expressing random processes where events occur as a whole. It's basically events over time occur as whole inseparable units that can't be broken down into smaller components until something happens. So until there's an interaction. So it's like thinking of that ball thrown through the window
Mhm.
as just being one event. It's interacting with air particles, but apart from that, the big interaction doesn't happen until it hits the ground.
Yeah.
And so do the math around that whole event. And so what that gives you is basically you're applying non-Markovian processes to your calculations. Um, and where the future evolution of a system depends not only on its present state, but also its history of past states. Um, and this is what basically allows more complexity ideas to be added right from the quantum level. And I I think, I don't know if I understand it, but it does apply to even up to the concept of Markov blanket. Now, when I first heard him talk about this, I said, oh no, Markov blankets also have this problem. But luckily, I even used AI and looked it up on Copilot. And luckily,
Mhm.
Markov blankets don't rely entirely on simple Markov chain processes. They can include non-Markovian processes in them. So it's the where non-Markovian probability refers to systems or processes where the future depends on both present and past states. So in this sense, a Markov blanket can be something that's described over time as having children that kind of retain a, a longer configuration space that you can regard as having more of a memory state than you would if you had a math of Markovs that always required, in a sense, every moment having explained every moment as a kind of a new instantiation of
Right.
the
Right.
blanket. So so this is a subtle but kind of a real problem when you're thinking about how it is that all this complexity, like for example, in assembly theory, an autopoietic system, how does it contain all of the information at once about all the predictive outcomes, all the paths that might be relevant to it, all kind of jumbled up into one basically physical configuration of the system. And in a way, it's there, but in another way, it is kind of relying on past events
Mhm.
in a more constructive and immediate way
Yeah.
um, that that make a difference. Um, so um, it lets you do, and then it lets you, I think, better grasp the idea of like the Markov blanket surface as being something that adjusts as a whole to more distant things and more and past things and predicted future things without having to have that immediate physical interaction.
Mhm.
For example, it could do things with the incoming photons and then act on the basis of a prediction of where those photons came from and do something about it. And this becomes seeing. This becomes literal observing. Uh,
Oof.
special adjustments to just these certain photons versus another, and you get something like color subject experience subjectively. Um, so
Ah.
yeah, so I don't know. For me, in in an odd way, I had talked in the last, I guess, 2 episodes ago about Ralph Stacey and how he had a critique of autopoiesis, where he said, "Well, autopoiesis only works if the future is somehow tied in as a component into the structure of the autopoietic system itself." And the same
Mhm.
goes with the past. And he said, "Well, this is a critique. This is impossible." Well, no, future prediction and past memory are possible given this physics. And
Right.
so
Right.
at that, from his critique, I ripped up my dissertation and chucked all of autopoiesis out of it.
I know. And
Now,
now
now I can put it
we're
back.
debunking Stacy. So
Yeah, I mean, he's right in a way. He was actually referring
he
to,
was right for his time without all
yeah,
this new information that
and it is valid. You could go back to that episode, which I don't have in front of me, but he does make valid critiques about not everything is a system, not everything is an
That's
operating
right.
system. So social order, social organizations don't have to be living systems in themselves. They could be made by living systems,
Yes.
but still described largely perhaps in these Markov blanket terms and
Yeah.
other even constructor theory terms. So we got
Wow.
new language, and I've been obsessing about it.
Well, this is a tour de force of extemporaneous thinking with a few notes about the emergent, and what's emerging in part is you
Yeah,
in your grasp of things,
yeah,
and helps me and anyone else listening to get not necessarily the little tiny details, but the rhythm of it
yeah,
that you've talked about. It builds and builds and builds, and then I think we're all going to be wanting to wrap ourselves in Markov blankets tonight to stay warm, because that's such a consistent um, model for us to organize our thoughts around. All
yeah,
those little babies underneath it, and the overall, and all of these going on constantly. I think we're onto something. You're onto something, and I'm recording it. And I can't go much further on time, because it exceeds any listener, except if they listen and stop and then come back to it.
Yeah, I might take another listen, because I'll probably keep incorporating these ideas into something that's much more simple to understand, like the nature of human emotions.
Yeah, well, we're moving in that direction again. We started with that way back in the first discussions of conversation, and how people are either drawn together or move apart according to their moment-to-moment turns of talk and all the things that go on. And so, in a way, what we look at as us living and adjusting constantly to change in the world is not unlike something that you can't even see at the subparticle level. There's the same kind of things going on.
Yeah.
We're all trying to keep going.
Yeah. So maybe we'll step back from physics. I resist the urge to throw in something about the nature of time and whether the universe is has a mirror universe that's like an anti-universe. Not one where there's evil versions of ourselves.
Well, that would be fun to talk about too.
But we'll see.
So,
but
this has been
something more social.
No need to rush back. This is looking at a level I've never thought about. So, and I think that's very much the purpose of the Practice Podcast. It has a question mark. Practice.
Mm-hmm.
And this is a way of looking at the unseen but very fascinating dynamics of something approaching life, and then life going across the threshold. I think it's very cool. So thank you, Dave, again. We'll do this.
Thank you for
soon,
listening
so
to
we
the
can
Practice
pick up on
Podcast,
the
conversations
threads that you
probing
may
the nature of
Thank you
practice.
again.
If you'd like to hear more, go to Automatic, Spotify, Apple Podcast, or YouTube. And please consider purchasing our book on practice as a way of being at mylibrary.world. It's a digital book with lots of features that you do not see in a conventional book. So once again, thank you, and I look forward to you listening again.